Hi, this is a mini lecture on brittle deformation in Earth's crust in the form of faults. Brittle deformation refers to the rocks in the Earth's crust responding to stresses, typically tectonic stresses, that is in the form of brittle, permanent strain. So in other words, the rocks break rather than fold. Examples of brittle deformation in Earth's crust include joints, veins, and faults. And joints and veins are when the rocks, fracture, but there's no movement along the fracture surface, so maybe they just kind of pop apart. And so these two pictures here on the slide show examples of veins that have since filled in with water solution, and minerals have precipitated out, and so that preserves the joints and the veins in the rocks. Faults are a little bit different in that they're fractures in Earth's crust, but there has been motion along the fault surface, whether that motion is up, down motion, or sideways motion, or some combination. So faults are common at plate boundaries because that's where the rocks are experiencing maximum stress from tectonic motion. They occur at all types of plate boundaries, but not just right at the boundary. I mean, for example, faults are not what constitute the plate boundaries, but they occur near plate boundaries because of the motion and the stresses on rocks. So when we talk about faults, we have to be able to describe the type of motion along the fault, which will help us then to describe what caused that type of faulting. So there's a couple of things that we talk about. So how do we recognize faults when we're out in the field? So if we're walking along our surface, we might notice that there are two rock units juxtaposed, and we might notice that there's some sort of offset between the two, and recognize from that we're encountering a fault. So where the fault plane intersects land surface, a horizontal line, this is called the strike of the fault. And if we were going to map out the fault, then we would, note the compass orientation of the strike. For example, it's north-south, or east-west, or northeast-southwest. But it's a horizontal line that intersects land surface. But another thing that we would note, especially if we can see down inside of the Earth and we can see the fault as it goes deeper below our surface, we'll notice that the faults typically are not straight up and down. They are not vertical. They are at some angle. They are dipping from the horizontal at some angle. So this is called the dip of the fault. So when we think, these terms are important when describing faults because sometimes this motion along fault is a motion that's parallel to the strike, so a kind of a side-to-side motion. And sometimes the motion is something that's parallel to the dip of the fault, so sliding or slipping up and down the dip of the fault. So in this picture here, we're seeing a kind of a cartoon drawing of a fault, and if we were walking along land surface, we might recognize that it's a fault because we see that one block of Earth's crust is sticking up further than the other block, and so there's been some motion up and down the dip of the fault. So the fault kind of divides the crust into two sections. The block on this side we call the footwall block, and the block on the other side we call the hanging wall block. And again, this kind of cartoon helps to illustrate why it has these names. Sometimes when faults are created, water can infiltrate along these fractures, and over long periods of time, valuable mineral deposits can precipitate out from the watery solution. So sometimes when we recognize a fault, we start digging down along the fault plane. We might be able to uncover, like a gold vein or something like that. And so this picture shows a miner, and as he's digging out along the fault and walking down the fault, he is standing on the footwall block side of the fault. And as he gets deeper and deeper below our surface, it gets darker and darker, and he hangs a lantern. So it's hanging on the hanging wall block side. So again, this is a fault, the fault plane, the block of earth, the block of the crust that a person would stand on is called the footwall block, and the other side is called the hanging wall block. So that helps us to describe the motion along this fault. So we can say, for example, that the footwall block moved up, in this case, relative to the hanging wall block. Another way of saying that is that the hanging wall block moved down relative to the footwall block. So the motion has been parallel to the dip of the fault rather than parallel to the strike of the fault. So this is a real photograph of a fault, and we can see a side view of it. So maybe this might be exposed because of erosion or because of construction. Maybe they built a road through this area, and now we can see the side view of the layers in the earth. So these are rocks that were formed horizontally, sedimentary rocks. And so, for example, this black layer here used to be next to this part of the crust. But a fault formed. Here's a side trace of the fault. So we can see that this block moved up relative to this block. So is this side of the fault, is this called the hanging wall block, or is it the footwall block? So this is a hanging block. So the hanging block moved down relative to the foot block, or the footwall block. So this is a picture of a scarp left behind by a fault. Sometimes we can see these at land surface before they erode away. So this would be evidence that we can tell by the dip that this is the footwall block that has moved up relative to the hanging wall block. There's other evidence that faults exist or have existed in the past, things that we won't get into for this part of the course, but there could be change in the mineralogy. The rocks can become slightly metamorphosed, so the minerals kind of get smeared out along the fault plane because of the tremendous amount of pressure. So what types of stresses cause this motion? So the Earth is responding to stress by the crustal rocks are breaking, but then there's motion along the break, or motion along the fault. So we can talk about the stress that's applied to the rock in three different, as being three different types of stress. There's a directionality to the stress. So for example, near a convergent boundary, the crustal rocks are compressed. So the side to side kind of squeezing motion. And so the compression, it's kind of a side to side squeezing or compression, results in faults where the hanging wall block moves upward relative to the footwall block. And this type of stress would be most common at convergent boundaries. Then tensional or extensional stress is when the crustal rocks are being pulled apart laterally. So it doesn't pop open. If it slides along the fault, then it results in the hanging wall block moving down relative to the footwall block. So that type of faulting is a result of tensional stresses, which are common at divergent boundaries where rifting is happening. And sometimes the motion is less of an up-down dip-slip motion, but more of a sideways strike-slip motion. And this would be the result of shearing stresses applied on either side of the fault. So to notice the offset, you'd have to look at it from the top. And you can see that there's a side-to-side motion. It could be to the left or to the right. So of course, this type of stress, the shearing stress, is common at transform boundaries, and it results in this type of faulting. So when we talk about motion along faults, we talk about the movement that occurred, the displacement, as being a slip. So when the movement is along the dip of the fault, up or down, we call it dip-slip faults. But we've seen that there's two major types of dip-slip faults, the kind where the hanging wall moves up and the kind where the hanging wall moves down. Compression, due to tension. The other type of slip would be strike slip, the side-to-side motion due to shearing of the rocks. So just a little bit more about the dip-slip faults and the different types of dip-slip faults. again, if the hanging wall block moves down, and it doesn't matter the orientation, it's the one that kind of hangs over. If it moves down, we call that a normal fault. And so in this picture here, it's showing the hanging wall block moving down relative to the footwall. And we can notice it if we see kind of a side view of the faults, profile view. We can also notice it if the fault plane is exposed above land surface, and we can see the direction that it's dipping. So normal faults result from tensional stresses that pull, stretch, and therefore elongate the crust in the lateral direction. But that elongation of the crust side to side also results in a thinning of the crust. So you can see here that originally this block of the crust was this thick from the top of the green to the bottom of the pink layer. But because of normal faulting, some sections of the crust get thinner. And this is what's happening in divergent settings when you have rifting, and this thinning of the crust can allow hot rocks to melt because they're under less pressure, and you get lava that can pour up along these faults in some cases. So the opposite, when you have compressional stress, you can reverse faulting. So when the hanging wall block moves up along the dipping fault plane. So this picture here shows the hanging wall block moving up, and we can see that this type of motion has occurred here because this layer used to be continuous across the fault, but now you can see it's moved, the side has moved up, the overhanging side moved up. So that's a reverse fault, and that's due to compression. So compression shortens the crust laterally but causes it to be thicker vertically. So reverse faulting happens at convergent settings, where plates are moving towards each other. We also know that at convergent settings, if there's oceanic crust involved, then you get subduction as well, and that also accommodates this kind of compression or shortening of the crust. But imagine that if we're talking about continental-continental convergence, where there's no subduction happening, and so the crust continues to be squeezed in this direction, so you might get more reverse faulting happening there, causing increased thickening of the crust to accommodate the shortening. If there is no subduction and or the rate of compression is great, then often the dip of the fault plane will be very low angle, and so this is a type of reverse fault called a thrust fault. A thrust fault is the same thing as a reverse fault, reverse dip slip fault, except that it's a low angle reverse fault. And so this would be common at places where a lot of crustal shortening happens. And this is very low angle faulting here, thrust fault. You can also see another example of thrust fault. There's the footwall block. So this kind of red unit of rock used to be continuous with this red unit up here, but they have this low angle fault that's formed that's kind of squeezed this whole scenario in this direction. And then we have strike slip faults. There's no vertical offset, so when we recognize them, we have to see a displacement from above in order to recognize that strike slip faulting has happened. So there's two directions to strike slip faulting. It can be left lateral or right lateral. So in this diagram here, there's a block of the crust, and there is some straight line feature that crosses the fault. And so in this case, it's a dike, which is an intrusive igneous body, but it could be a road, a fence, a stream, or any kind of feature at land surface. You start to notice that there is a kind of break in the crust, and that this feature has been offset, then we can recognize that likely strike slip faulting has occurred. So imagine that this black line is, instead of being a dike, let's say it's a road, and this is a road that you take to school each morning, and one day overnight an earthquake happened. It caused displacement along the fault, and so as you walk along this road, you notice that when you reach the fault that the road does not continue straight across. And so in order to continue on the road, you need to make a left turn. to continue on the road. So that's one way to recognize that this is a left lateral strike-slip fault. And when you come home again, you have to make a left turn to continue. If the opposite happens, if you have to make a right turn because the displacement is to your right as you're looking across the fault, then we say it's a right lateral strike-slip fault. So faulting, right lateral, left lateral is the result of shear stress applied to rocks, and shear stress is the result of there's a stress that's a result of movement along transform boundaries predominantly. So transform boundaries produce a lot of shearing stress, a lot of strike-slip faulting in association with those types of boundaries. Probably one of the most famous transform boundaries where we see a lot of strike-slip faulting occurring near the plate boundary is the San Andreas fault system. So the San Andreas fault system is parallel to the boundary between the North American and Pacific plate in the western part of the United States. And we can see some features that have been offset across this fault. Here's a picture of a fence that is offset. It seems like a silly way to build a fence. But when the fence was built, it continued straight across. But it turns out there was a fault offsetting the fence, and as a strike-slip motion occurred, shearing stress resulting in strike-slip motion, then the fence basically broke and has been offset. So would this be a right lateral or a left lateral strike-slip fault? This is the fault trace. If you're standing at the fault looking across, you'll notice that the features have been offset to your right. So this is a right lateral strike-slip fault. So here's a stream that used to be continuous across the landscape here, and over long periods of time, because of motion along the San Andreas fault, this stream has been offset. So this would be an example also of right lateral strike-slip faulting.